Hey everyone, welcome to another video of quantum field theory. In today's video, we'll be proving Haag's theorem. Haag's theorem is a theorem which states that the interacting picture pretty much does not exist. So let's actually prove this theorem. But before we prove this theorem, let's talk about what we talked about in the last video. So in the last video, we derived the Gelman-Low theorem. This is the Gelman-Low theorem over here. It relates the VEV of the time-ordered endpoint correlation functions in the Heisenberg picture with the VEV of the endpoint time-ordered correlation functions in the interaction picture with the unitary operator. And we would derive this relation by saying that, okay, let's assume that there is some time t where the Heisenberg picture field, which recall is an interacting field, equals the interacting picture field, which is a free field. So we assume that there was some time where this was true. And if that's the case, that implies that there is a unitary operator that relates the interaction picture free field with the Heisenberg picture interacting field, where U is equal to this over here. Technically, there should be some time ordering here, but we're going to ignore that for now. Now, what Haag's theorem says is that there actually is not a time where this is true, which implies that there is no U, there is no unitary operator that relates the free field with the interacting field, which means that this relation is not true. So let's actually prove that. So we should first note that the vacuum state is what's called Poincare invariant, which implies that the transition operator acting on the vacuum state gives us the same exact thing. And by the way, the transition operator, right, it's from quantum mechanics. It's going to act on some wave function psi of x and give us out psi of x minus a, which means it shifts the wave function by some amount a. Now, if psi of x equals psi of x minus a, that means that the state psi is invariant under the translation operator. This is only going to be the case if the wave function is a vacuum wave function, which means this is only true if we have a vacuum state. And this makes sense because if we have no particles in our state, if we move around our coordinate system, well then the state's going to look the same because there's no particles, right? But if there are particles, we could have a wave function that looks like this or something. And if we were to shift around in our coordinate system, what's going to happen is that the state is going to look different because we have a different psi of x if we shift around our coordinate system. So the translation operator acts on the interacting vacuum state in a similar way. That being it does not really act on at all. We get the same thing as well. Note that for the interacting vacuum state, we have to use the interacting transition operator, right? So this subject not over here means that it's a free operator. But if you don't have that subject, you mean that it's an interacting operator that will act on the interacting states. So by the way, psi naught is defined as a free field, where psi by itself is defined as an interacting field. Note that psi h is also interacting, whereas psi I is going to be free. So the transition operators act on our free and interacting quantum fields in this way over here. Again, we see that for the interacting we see that for the free field, we're going to have T naught, because that's the free transition operator. And now we can use the unitary operator to write the free field and the interacting field, right? Where in this case, we're going to use psi naught, since the interacting picture field is a free field, and then we're just going to use normal psi by itself, since the Heisenberg field is a interacting field. We can just like look at this lower equation. We can multiply both sides by u conjugate and u, so both sides by that. And since phi is this over here, this means that this is going to equal this over here, which implies this is going to be equal to this over here. And by doing some matching, this implies that T naught A acting on U equals U acting on T A. So this implies this. So you derived a very important relation, right? The free translation operator acting on the unitary operator is going to equal the unitary operator acting on the interacting translation operator. We can look at how the unitary operator acts on the interacting vacuum, and we can just write that out like this. We can insert the interacting transition operator acting on the interacting vacuum, because the interacting vacuum is invariant under those translations. And then we can just use the formula, this one over here, and say that this is just equal to T naught. I'm going to omit the of a U T naught acting on the interacting vacuum. And now we've derived something really important. So this means that this quantity over here is invariant under the free spatial translations. But we just said earlier that the free vacuum is invariant under the free spatial translation, right? So that would mean that this over here is just the free vacuum. And this implies that the interacting vacuum is the conjugate of the unitary operator acting on the free vacuum, because the unitary operator is unitary. So you can just multiply both sides by U conjugate, and then this would go to 1 since it's unitary. So now what we can do is we can look at the product or the inner product, and this inner product is going to be equal to this over here because of this relation right over here. And we can also look at the inner product of this. We can look at this inner product as well. And we know that this inner product is going to be equal to the vacuum state acting on the interacting vacuum state because of this right over here, which implies that this over here and this whole thing conjugated is just going to be U, right? We're just going to have U of T naught. And since we have the same thing here, and these are equal, this implies that the interacting vacuum state equals the free vacuum state. And I don't know why, I just find this like really funny. It's like, you know those like proofs online of like 1 equals 0? This kind of reminds me of those proofs. We've just proven, right, that the unitary operator, right, that relates to the interacting fields with the free fields, this unitary operator will imply that the interacting vacuum state equals the free vacuum state. This over here is saying that if this is a free field, right, this will also be a free field. The Heisenberg picture field will also be free, because since the interacting vacuum state equals the free vacuum state, that would mean that the interacting quantum field is a free field, right? So this means that this unitary operator, right, if this is free, this will also be free as well. And if this was interacting, then this would be interacting as well. So the unitary operator cannot transfer us from a free field to an interacting field. It can only give us back the same thing. So we can't use a unitary operator to relate the free field and the interacting field. So this is kind of telling us that the interaction picture only exists when there are no interactions, right? Because if there are no interactions, the interacting vacuum state is just the free vacuum state. We should actually be using the free vacuum, making this whole thing a trivial relation. This is also I over here. So basically, Haag's theorem is just saying that if there exists a unitary operator that relates to the interaction picture field with the Heisenberg picture field, well then if the interaction picture field is free, then so is the Heisenberg picture field, right? So the unitary operator cannot take us from free fields to interacting fields and vice versa. It also says the converse. If this is interacting, then this must also be interacting. So it's telling us that the interacting picture pretty much does not exist if we have interaction. If the Heisenberg picture fields are different from the interacting picture fields, that must mean that this unitary operator here must diverge. And this is telling us that if we're to expand out the unitary operator in a perturbative series, we should be met with infinities. And indeed, we do get infinities. The series, if we were to expand e to the minus I, if we were to expand this in a Taylor series, you're going to find out that the series diverges. And you guys might ask, what about renormalization? I haven't talked about renormalization yet, right? But for those of you guys that do know renormalization, I guess might say, oh, that's going to make this series converge, right? That's not true. Renormalization only makes each term in the Taylor series converge, right? However, the whole series still diverges. It's still what's called an asymptotic series. So renormalization cannot sidestep Haag's theorem, because Haag's theorem is what's called non-perturbative. We proved this theorem without making use of any perturbative arguments, right? We didn't expand anything in some sort of perturbative series, which means that renormalization, which is a perturbative thing, it cannot make these infinities go away completely, right? So in a way, trying to use renormalization to go away from Haag's theorem is like trying to play a jump spell on a hog rider. It's just not going to do anything. So Haag's theorem is a very important theorem in the rigorousness of quantum field theory. It's telling us that we cannot use the interaction picture rigorously because the interaction picture only exists when we don't have interactions, i.e. when the interaction vacuum state equals the free vacuum state. By the way, I didn't talk about this in the last video, but the reason why we go from infinity to infinity for the evolution operator, this is going to be u of infinity, or really this is going to be u of minus infinity. The reason why we go from asymptotic times is that recall that in the LSE formula we were dealing with asymptotic particles, right? So that's why for the unitary operator we actually want t and t naught to be infinity and infinity and minus infinity. So let's leave it at that note. Thanks for watching, and I hope you guys have a great day. Bye.